Swayam Prabha. Digital India. Educated India.
Welcome back to the course Mechanics of Solids. So, in the last lecture basically we talked about several things about the analysis of the slender member, okay, to find out the bending moment and shear force, right. So, today we will be taking couple of numerical examples, okay, on the same topic like determination of shear force and bending moment as well as shear force diagram and bending moment diagram subsequently. Okay. So, let us take this problem today, the first problem, that is draw the shear force and bending moment diagrams for the following case. So, this is the beam ABC is a beam which is having the overhanging part BC. Okay. It is supported at point A and point B, simply supported with overhanging part BC and under the action of the uniformly distributed load W naught. Okay. So, now we need to find out the shear force diagram and bending moment diagram for this particular beam. Okay. Now, what should be my approach? The first step for this problem will be to draw the free body diagram, right. So, if you want to draw the free body diagram basically, so you generally do or generally replace the supports with the reaction forces like RA and RV. Okay. There is no horizontal reaction at A because there is no horizontal external forces. Okay. So, now my next job is to find out the reaction or the reaction forces RA and RB by satisfying the equilibrium equations. Okay. So, if you satisfy the equilibrium equation, if you consider moment equilibrium with respect to 0, you will find out RB equal to W naught L plus A whole square by twice L. Okay. And similarly, if you consider summation of all the forces in y direction. So, this is your say y and x. Okay. So, loading is in xy plane. So, if you consider the summation of all the forces in y direction is 0, then basically you will be getting R A equal to W naught L square minus A square by twice L. Okay. So, these two things we are getting from the equation of equilibrium. Fine. Okay. So, now what is my next step? We will be choosing few steps, I mean few sections, okay, few sections by which we can define the shear force and bending moment equations or the expressions for the whole beam. Now, how many sections we need, how many minimum number of sections we need for this problem to tackle? By seeing this problem, it is very clear that two sections will be required. One section will be between A and B and the second section will be between B and C, right. So, that is quite obvious. So, I am taking two sections, section 1 and section 2. Okay. And then I am drawing the free body diagram for section 1. So, I am considering the left hand part of section 1. So, that will look like, so section 1 which is varying 0 to L. Okay. So, this is the free body diagram. This is my shear force V, this is my bending moment MB, okay, and this is W naught. Okay. So, this is your section 1 fine. Okay. Now, if you want to find out shear force and bending moment, you can find out by satisfying the equation of equilibrium. Okay. So, equations of equilibrium, if you satisfy, then basically first one is your Fy equal to 0. So, I can simply write Ra plus V minus W naught into x equal to 0. So, from there I can get V equal to W naught twice Lx minus L square plus A square by twice L. Okay. So, this is the expression for the shear force which will find out or which will determine the shear force between 0 and L, okay, for section 1. So, section 1 is valid between 0 and L or 0 and L, right, in the problem. Okay. So, now at x equal to 0, your V at x equal to 0 is equal to simply this part will be 0, simply minus Ra, which is nothing but minus W naught L square minus A square by twice L. Okay. And at x equal to L, your V is equal to, you put x equal to L there, you will be getting W naught L square plus A square by twice L. Okay. So, you have got the magnitude of your shear force at two extreme points, okay, at x equal to 0 and x equal to L, fine. So, that will be required to draw the shear force diagram, okay, later on. So, now if you look at this equation or these values, right, at x equal to 0, V is simply minus of this, okay, that means the negative value, and x equal to L, the magnitude of V is positive value, right. So, the magnitude of shear force is changing from negative to positive from 0 to L. So, there must be some point between 0 and L where shear force is becoming 0, that is for sure, because if you want to travel from negative to positive, you must cross the 0 point, right. So, we need to find out where the shear force is becoming 0 between 0 and L. So, to do that expression of shear force, we can put simply that thing equal to 0. So, if V is 0, okay, then I can get W naught twice Lx minus L square plus A square by twice L equal to 0. From there I can get x equal to L square minus A square by twice L. So, that means at x equal to L square minus A square by twice L, basically your shear force is becoming 0, okay, fine. So, now these are the informations we have extracted from that expression, okay, whatever we have derived based on summation of Fy equal to 0. Now, we will be considering the moment equilibrium, okay. So, we will be considering the moment equilibrium. So, let us take the moment equilibrium equation, summation of m equal to 0. So, we can simply write mb, if you look at here, mb plus W naught x into x by 2 minus R A into x equal to 0. Okay. So, from this I can get M B equal to W naught x L square minus A square minus L x by twice L. Okay. So, at x equal to 0, your M B is equal to 0 from this expression. Fine. We are going to find out the bending moment at two extreme points. At x equal to L, this is, if you put x equal to L here, you will be getting minus W naught A square by 2. Okay. If you see here, if you put M B equal to 0, okay, if you put M B equal to 0 in this expression, then from this equation it is very much clear that there are two values of x where the bending moment is becoming 0, yes or no. One point already we have obtained, that is at x equal to 0, but another point is yet to obtain, yes or no. So, if you look at this expression, so that if you put bending moment equal to 0 here, at x equal to 0 the bending moment is becoming 0, that is already obtained, but another point you must get from this where again the bending moment is 0, right. So, let us find out that point. So, we are just simply putting W naught x by twice L, L square minus A square minus L x equal to 0. So, from this I can get M B at x equal to 0 0. So, from this I can get x equal to 0 or L square minus A square by L square. Okay. So, that means M B at x equal to 0 is 0 and M B at x equal to L square minus A square by L is also equal to 0. Fine. So, now what you are getting? You are getting it is starting from 0 and then it is gradually building up and then again it is becoming 0 and then it is going to the other side. Okay. That kind of, say, I mean picture, some hazy picture, not very clear picture you are getting, some hazy picture you are getting, right. So, that this could be the possible variation of M B. So, there must be some point, okay, where M B is becoming maximum, is not it. There is some, there must be a point, that is there must be some value of x where the bending moment is becoming maximum, because during this variation somewhere the bending moment will be touching the maximum value. Okay. Let us find out that. So, if I want to find out that, so for that we simply do, as you know, to get that maximum bending moment. So, therefore, your bending moment maximum is happening, if you do that, you will be getting x equal to L square minus A square by twice L. So, at that x value, basically your bending moment is becoming maximum. Okay. If you do that, I mean very simple thing, right, that derivative of that equation. So, the maximum value of your bending moment therefore will be at x equal to L square minus A square by twice L is equal to W naught L square minus A square by whole square by 8 L square. So, this is the maximum value of bending moment which is occurring between 0 and L. Okay. So, these are the informations will be required when we will be drawing the bending moment diagram. Okay. Now, so this is all about your section 1.1. So, we have got the maximum information from section 1.1. Now, we need to solve the section 2.2. So, let us solve that thing. So, your section 2.2 section 2.2. So, for section 1.1 we had taken the left hand side of our section, right, for our convenience, as you know. So, this convenience how how your problem will be getting a little bit easier. So, that thing you have to judge, and this judgment will be coming from more and more practice and more say solving of the problem. Okay. So, for section 2.2 we will not be coming from left, okay, rather we will be taking from right, because that will be more convenient to find out or to analyze. Okay. So, let us take the right hand side of section 2.2. This is your section 2.2. Okay. This is your V, all directions are positive. Okay. This is your section 2.2. This is your W naught. Okay. And this distance is L plus A minus x. Agreed? Because section 2.2 is taken x distance away from A. So, this distance will be L plus A minus x, fine. So, again, and this section is valid between L and L plus A. Okay. So, again we will be doing the same thing, we will be taking summation of f y equal to 0, that gives me minus V minus W naught L plus A minus x, okay, equal to 0, from which I can get V equal to minus W naught L plus A minus x. So, at x equal to L plus A, your V is simply 0, and at x equal to L, your V is equal to minus W naught into A. Okay. Now, we will be taking the moment equilibrium, we will be considering the moment equilibrium. If you consider that, so minus MB minus W naught L plus A minus x into L plus A minus x by 2 is equal to 0. So, from which I can get MB equal to minus W naught L plus A minus x whole square by 2. Okay. So, for this, at x equal to L plus A, your MB is equal to how much? Simply 0. Okay. And at x equal to L, your MB is how much? Minus W naught A square by 2. Okay. Fine. So, these are the information we have got from section 2.2. Now, let us draw the bending moment and shear force diagram. So, first we will draw the shear force diagram. So, shear force diagram we are drawing. Okay. So, this is your baseline, this is A point, this is B point and this is C point. Okay. So, your shear force diagram will be looking like this. Okay. This is negative, this is positive and this is again negative. This is the value already we have calculated, L square minus A square by twice L. This distance where shear force is becoming 0, that also we have calculated. If you look back the solution, and this part already we have calculated for section 1-1, it was coming W naught L square plus A square by twice L, and this part will be coming from section 2-2, that was minus W naught into A. So, this is your typical shear force diagram. Okay. Similarly, I can draw the bending moment diagram. Let us draw the bending moment diagram. This is say A, this is B and this is C. Okay. Generally, we draw shear force and bending moment diagram just below the actual say free body diagram of the beam. However, due to the space restriction in the board, I am drawing like this in separate way, but generally we show one by one. So, first the free body diagram of the beam and then just below SFD and then below of that BMD. Okay. Fine. Anyway, so that's not an issue. Generally we show like that. Okay. So, now for bending moment at A, what was the value of bending moment? Simply 0, and that has gone some maximum value and becoming 0 and getting some value at B, and again it is at C it is 0, right. So, this is your maximum value which was calculated where the bending moment was maximum, that was calculated as L square minus A square by twice L. Okay. And this maximum value was calculated as, if you recall, W naught, this is positive and this is negative, W naught L square minus A square whole square by 8 L square. Okay. And this was the value calculated as W naught A square by 2. Okay. So, this is your typical BMD. Okay. I hope you have understood the process involved in this kind of say problem. Okay. So, we have got SFD and BMD for this simply supported with overhanging part beam. Okay. So, I will stop here today. So, in the next lecture we will be taking one more say numerical problem, and then we will be switching over to the next chapter, that is torsion. Okay. Torsion in circular shaft. Okay. So, I will stop here. Thank you very much.